Hi everyone, so we've been through the pure and we're now on to statistics and mechanics. So we will go through, there's not so many questions in the paper, so there won't be quite so many questions in each one of these videos. We'll still do it over 3 though and take our time, and I will talk it through the way I think of it, and hopefully that'll help you for anything that you weren't able to do. There's some nice questions in here. Okay, off we go. Right then, so first part, we've got these 55 managers and 495 cleaners, but they just want to know what's meant by a census and one disadvantage of using it now. Well, a census involves asking everyone in the population. And then the disadvantage would be, as there are 550 people in the company, this could be very time consuming or expensive. Right, part B. To collect data, the researcher, not the decider, decides to give a questionnaire to the first 50 cleaners to leave at the end of the day. State the sampling method. So this is opportunity sampling, when you just take the opportunity to have the first ones that are there, sometimes called convenience as well, but opportunity is the one they're really looking for. Give 2 reasons why this method is likely to produce biased results. So 2 reasons. One of them is it's just said 50 cleaners, and there are 2 types of people in the company they've told us about. So no managers are involved would be one, and the other is if they leave in a group, they may all be working on the same shift or something, maybe working the same shift. Or you could say belong to any group of similar opinions. So, I mean, you could say anything. You could say that they're all friends, something like that. That would do it. You could say that you're more likely to get because men tend to sort of become friends with men. You may get an unequal split of men as to women, and that sort of thing would all be okay as well. Right. So then we're on to the last part, which is explaining how you could select both of these samples. So a systematic sample, the first thing to do, 550 divided by 50 equals 11. So what you would do is you would make a numbered list of all the employees, and then randomly select one of the first 11 on the list, and then take every 11th on the list from there. So that would be a systematic sample, and for your stratified sample you need to have managers and cleaners separated to make sure that we get the right mix of them. So managers are going to be 55 out of the 550 we've got all together, times by the sample size, which is 50, and that would give you 5. That should tell you that you need 45 cleaners, but then if we just say cleaners is 495 out of 550 times 50 is 45, and then use a random number generator to select 5 managers and 45 cleaners. And that's that one. Right, what's not to love in a Venn diagram question, hey? So, show the probability that the student reads more than one magazine is 1/6. Well, there are two areas where you've got an intersection of two magazines being read, there and there. So you have got for part A, you've got your 2 out of 30 plus your 3 out of 30, making 5 out of 30, which equals 1/6. That's all you need, really. You've got 30 altogether. You could show all of those all adding up to 30 if you liked. Part B, find the probability that the student reads A or B or both. So that is those two and those ones, isn't it? So we are saying 4 plus 2 plus 5 plus 3 out of all the people who are there. If you add all of those up, as I said before, that is 30. Add those together, what have you got? 6, 9, 14 over 30, which is 7/15. Does not matter if you haven't simplified it. Part C, write down the probability that the student reads both A and C and explain what this probability tells you. Well, there's no overlap between A and C, so the probability is 0. And then all you need to write there is no one reads both A and C. Right, part D. Given that the student reads at least one of the magazines, find the probability that student reads C. So if you're given that it reads at least one of the magazines, that means we know it can't be any of those 10. So we've just got 20 left. So it's going to be something out of 20. And C is the 3 and the 6, isn't it? So 9/20 is part D. It's all been pretty basic so far, but E is a little more challenging. Determine whether or not reading magazine B and reading magazine A are independent. Now we can work out B and C is written as B intersection C, isn't it? And we've got B intersection C as being 3 out of everything that's there is 30, haven't we? Now, in order to work out whether or not that is real, which is also, we could call 1 out of 10. The other thing to think about, and if you look in your formula booklet, you will see that it says the probability of B intersection C is the probability of B multiplied by the probability of C happening. And this is the acid test for whether or not these things are independent. So that's going to be the probability of B is 2, 5, 10 out of 30 multiplied by probability of C is 9 out of 30. Multiply those together and we get 9 out of 90, which is 1/10, isn't it? So therefore that is the same. Yes, they are independent. And that's all we need on that. Right, question 3. The first 4 marks, I don't think you'd have had too much difficulty over. The last 4, it's going to take a bit of a shift. It's going to be using maths that we've done before, but not quite in this context. So I'm really glad this question came up, because it allows us to explore something in the use of logs that you may not have considered. Anyway, state clearly the conditions under which it's appropriate to assume that a random variable has a binomial distribution. So there are 4 conditions that we must always have. So one is that only 2 things can happen, either success or failure. It's just 2 things that you can have. So as long as you've got exactly 2 things that can happen, and then probability of them adding up to 1, you're okay. Next thing is there are a set number of trials. So you have to know how many times you're going to have a go at doing this trial. The probability is the same for every trial, and each trial is independent of the others. You can have slightly different ways. You could have said it's 2 possible outcomes or something for that one. Set number of trials, sometimes people like to use the letter n when they say that as well. And then to say that n is the same every time is something that they might then say there. But the important things are those 4 things. You must have all of them for 2 marks. You've got to have at least 2 of them for 1. Right, part B. Right, so we've got a door-to-door canvasser. I did this once. It's can be a soul-destroying thing, but can be great fun as well. Tries to persuade people to have a certain type of double glazing installed. It wasn't double glazing, it was restaurants I did it for. Anyway, the probability that his canvassing at a house is successful is 0.05. Now in reality, I don't think you could use a binomial for this, because if you have success at one door, I know for a fact you're more likely to have success at the next door, because your morale is up and you can get on a really good run, and you can be, likewise, if you've had lots of failures, it just gets less and less likely. However, forget what I've said there, because they've told us that it's always going to be the same, so we're going to say it's the same. So we've got our binomial distribution. Now they haven't asked us to set us up this time. It's always a good idea to write it. We've got 10 houses that he's canvassing, so it's happening 10 times. The probability is 0.05, and he wants a probability of at least 2 successes. Now the expected outcome will be 10 times 0.05, which is actually just 0.5, isn't it? So you're expecting him to be successful at half a house, which isn't great, is it? So if you've got 10 houses, we're looking at doing something like that, with that being 0.5, and we are thinking, right, if we're up to 2, what's the probability that we're in that part there? And in order to do that, we can do all of this on the calculator. Go to menu, statistics, distribution, binomial, cumulative distribution, BCD. The lowest result we want is 2. The upper is 10 because we've got 10 trials. The number of trials is 10. The probability is 0.05. We press execute twice and we get a probability. So if we write this as the probability that x is at least 2 is going to be 0.0861. Remember, they like to have 4 decimal places, don't they? If you've done it to 3, and then fine, give it to yourself, it doesn't matter. And that's part B. Now part C is where it gets a little trickier, because it says calculate the number of houses you must canvass so the probability of his getting at least one success exceeds 0.99. So we're no longer talking about just canvassing 10 houses, because it's only the most likely thing to happen is that he gets a half of one. So it's nowhere near 99% chance of him getting one. So we are thinking about a new distribution here. So often talk about why when you're thinking about a new one, and we don't know how many trials it's going to be. So we could call that n. But we do know that it's a 1 in 20 chance of any house that the canvasser goes to that he will be successful. So at this point we start to think about, well, what do I know? And the thing is, at least 1 means that we could be, we don't know how many more than that we're talking, but what we do know is that it's not 0. So the probability of it being 0 houses we can work out, because this is asking us for the smallest number where the probability of y is going to be greater than or equal to be 1, to be more than 0.99. So therefore we are talking about the probability of y being 0 has got to be less than 0.01. So we start thinking about that. Forget about the inequality for a moment. If we were going to work out how many times it was going to be, we're saying and the chance that it's 0 is 0.95, isn't it? The chance that you're unsuccessful is 0.95, and we're saying how many times that, because every time if it was twice it'd be 0.95 squared, wouldn't it? If it's 3 times 0.95 to the power 3. So we're asking how many times would this have to happen and we still get an answer that is 0.01. Now what that means is, if you think about logs, log for 0.95 to the power of n is going to come through from there, isn't it? If you remember our good old logs, I always say 2 to the power 3 equals 8. So when we're talking about logs, we're saying, right, the log for base 2 in order to get 8 is 3. So that's what we're doing. And what we do now is just get the calculator, run back through, and now we want a base 0.95. So if you press maths and then log AB, put 0.95 in there, 0.01, press equals, and it says, and that gives us 89.78. So that is, it's going to take more than 89 goes, so it must be 90. So n equals 90. Now if you want to check this, I'd always say it's a good idea to check it in the exam. You could check it, couldn't you? Because we're saying, right, we're saying if our, let's put a new one here, if our binomial is going to be 90 attempts and it's a 0.05 chance, if I go back to my, I am wanting at least one upper 90. I've got 90 trials, that's my probability. What's it giving me? Probability is 0.9901. Now that makes me really confident that I've got this right, because it's clearly only just over a 99% chance of getting at least one success. Right, that is the first 3 questions all sorted out. Hope you enjoyed that as much as enjoyment can be, and that you scored quite well. And we'll carry on with the next few tomorrow.